Hello everyone and welcome to video number 3 in the Transformers course. In video number 2 we covered the transformer construction, and we know that the transformer consists of two coils magnetically coupled, electrically isolated. So in this video we are going to cover the principle of operation, an ideal transformer. Let's start. To understand the transformer principle of operation, let's go back to the 19th century and specifically in 1831 when Michael Faraday wrapped two coils on an iron ring. Faraday started by a DC source and nothing dramatically happened at that time. Once he got bored, he disconnected the mechanical switch and something strange occurred. The ammeter shows a brief deflection. At that time he realized that steady DC current was not the key. What mattered is the change in magnetic field. In other words, whenever the magnetic flux changes with time, there is induced current on the other coil. This simple observation becomes the foundation of the transformer principle. So, if an AC supply voltage V1 of t is applied to the primary winding N1 turns, so there will be a current I1 of t. This current is going to generate a magnetic flux phi, and according to Faraday's law, an induced voltage E1 of t will be produced, where E1 of t equals minus N1 d phi by dt. So minus is Lenz's law. Now we can calculate the induced voltage, which is N1, the number of turns of the primary winding, with the rate of change of this magnetic flux. This magnetic flux links the secondary winding and induces voltage here, E2 of t, according to the number of turns N2. And in this case, E2 of t equals minus N2 d phi by dt. If a load is connected to the secondary terminals, a secondary current I2 of t flows in the load, producing a load voltage V2 of t. From the transformer principle of operation, we are going to find important value for the transformers called transformer turns ratio. If our transformer is fed from a sinusoidal supply waveform, the primary induced voltage according to the AC sinusoidal excitation E1 of t equals minus N1 d phi by dt, and the flux is a cosine or sine function, so E1 RMS value equals 4.44 phi maximum Fs N1. Fs stands for the supply frequency and N1 is the number of turns of the primary winding. I proved this equation in the previous course, the magnetic circuit, and I'm going to add for you in the comments the link for this video. And the same flux is going to link the secondary winding. So according to the equation, E2 of t equals minus N2 d phi by dt. Hence, the voltage, induced voltage in the secondary winding, RMS value, equals 4.44 phi maximum, the same flux, Fs, supply frequency, but N2, the number of turns of the secondary winding. So in this case, we can say that E1 over E2 equals N1 over N2, we call it A, where A is defined as the turns ratio of the transformer, which is the relation between induced voltage in the primary winding and the secondary winding, or the ratio between the number of turns of the primary winding and secondary winding. If A is more than 1, so E1 is more than E2, and we call this transformer step-down transformer. If A is lower than 1, so E2 is more than E1, and in this case, that one is called step-up transformer. So now we know the relation between the voltages and the turns ratio. So what's the relation between the turns ratio and the currents? So if the transformer, our transformer, has a current in the primary I1 and the current in the secondary I2, so the magnetic circuit with the primary winding has MMF equals N1 I1 equals phi reluctance. And the same flux will be in the core, so the N2 I2 equals the same phi, same reluctance. From this one we can say that N1 I1 equals N2 I2, and in this case we can say that I1, the primary winding current, with respect to the secondary winding current equals N2 over N1, or 1 over A, the reciprocal of the turns ratio, not the turns ratio. So in conclusion, the relation between primary and secondary voltage is the turns ratio, while the relation between the primary and secondary current is the reciprocal of the turns ratio 1 over A. The turns ratio A equals the primary number of turns N1 to the secondary number of turns N2. We noticed in the previous slides, when you plot the transformer, you write the words ideal transformer. So what is the ideal transformer? Let's talk about the ideal transformer now. We will think of it as a perfect transformer. Theoretical model engineers use to simplify the analysis. In reality, transformers have some losses, but an ideal transformer assumes everything works perfectly. First, it is considered a lossless device, meaning there is no copper loss or core loss at all. This means all power input is transferred to the output. Accordingly, efficiency is 100%. Next, we assume there is no leakage flux, which means all the magnetic flux produced in the primary winding completely links with the secondary winding. In other words, coupling is 100% perfect. Also, ideal transformer assumes infinite permeability and zero reluctance, so the core allows magnetic flux to pass through with virtually no opposition. Also, the exciting current, which is the current needed to establish the magnetic flux, is considered almost zero. Another assumption, there is no electrostatic effects. Capacitance inside transformer can be ignored. Due to all of these ideal conditions, the applied primary voltage equals the induced voltage EMF in the primary side, so we can say that V1 equals E1, and similarly in the secondary side, V2 equals E2. So, transformer volt ampere, V1 which equals E1 and V2 which equals V2, so we can say that V1 over V2 equals N1 over N2. If we multiply that one by I1 over I2, where I1 over I2 equals N2 over N1, so we can cancel those together. So V1 I1 over V2 I2 equals 1. So the voltage ampere of the transformer, V1 I1 equals V2 I2. The volt ampere in the primary winding or the primary side equals the volt ampere in the secondary side. So now after we have the information about the ideal transformer, we need to start the analysis. So if the secondary side is connected to a load impedance Z load, like this circuit, what would be the relation between the voltage and current? So we can say directly Z load equals V2 over I2. That one is clear. But the question now, what is the value of this impedance seen from the primary side? If we like to do the analysis in the primary side, what is the value of Z load in the primary side? What we are going to do, we are going to transfer this impedance to the primary side. We call it Z load dash. Dash here means that we transfer this impedance to another side. So definitely this impedance has a relation with the primary voltage V1 and the primary current I1, or the transfer values of the secondary voltage V2 and the secondary current I2. We call it V2 dash and I2 dash. What is the relation between Z load dash and Z load and V1 and I1 or V2 dash and I2 dash? We don't know yet. We are going to do the analysis. But what we know that we have a relation between this Z load dash and the voltage in the primary and the current in the primary now. So how to calculate this referred impedance? We know that Z load equals V2 over I2 if it's in the secondary side or in the load side, but if it's referred to the primary, we call it Z load dash and has a relation between V1 and I1. So V1 over V2 equals N1 over N2 equals A, the Turner's ratio for the ideal transformer, and I1 over I2 equals N2 over N1 or equals 1 over A. So in this case, Z input equals V1 over I1. We can use the Turner's ratio equations. So that one equals AV2 over I2 over A equals A square V2 over I2 or A square Z load. So load impedance has a referred or reflected value seen from the primary side where Z load dash equals A square Z load. This means the referred impedance to the primary side equals the square of the Turner's ratio multiplied by the actual load impedance. Let us take an example. Step-down transformer is used to supply a lighting system from a 240 volt RMS source. The primary winding has 1000 turns. If the load voltage is 24 volt RMS value determined, the number of turns on the secondary winding, the transformer turns ratio, the primary current when the load is purely resistive and consumes 720 watt, the load resistance in the load side and referred value to the primary side. We are going to assume that the transformer is ideal, no losses. Given in this problem that the primary voltage is 240 volt, the number of turns of the primary winding is 1000 turns, and the secondary voltage is 24 volt, and that one is ideal transformer. So to calculate the number of turns of the secondary winding, we are going to use the Turner's ratio equation where V1 over V2 equals N1 over N2, and after the arrangement of this one, so we are going to find that N2 equals 100 turns. 1000 multiplied by 24 over 240. What about the turns ratio? So the turns ratio is straightforward now. N1 over N2 equals 10. So we need to calculate the primary current. To calculate the primary current, we need to calculate the current in the load side or the secondary current first, and then we are going to make a referring. So the load power is 720 watts, and we have a pure resistive load. So the current at the load side will be I2 equals P load over V2 equals 720 over 24 equals 30 ampere. Someone say that P should equals V I cosine phi. That one is pure resistive load. The power factor is unity. So what about the current in the primary? We are going to use a turns ratio equation where I1 over I2 equals 1 over A. So in this case, I1 equals I2 over A equals 3 ampere. What about the load resistance in the secondary side and the primary side? So the resistance in the load side will be V2 over I2, 24 volt over 30 ampere equals 0.8 ohm. We are going to use the referring equation, which is R load dash equals A square R load. So in this case, we have 10 square multiplied by 0.8 gives us 80 ohm if that one is referred to the primary. So we need to make a check that our answers are correct. So we have 3 ampere in the primary side, and the voltage in the primary is 240 volt. If we multiply 3 by 240 volt, that one is going to give us 720 watt. And also if we're going to use the 80 ohm, so 3 square multiplied by 80 is going to give us as well 720 watt. So we are correct. Another important point we need to cover in this video, the transformer rating. So the transformers are rated by their volt ampere. There is an important question we need to answer here. Usually industry employers like to ask in interviews. Why are the transformer rated in volt ampere, not in watts? If we look for different nameplates here, for example this one, we have the nameplate here shows 20 volt ampere transformer. Another one here 50 kilovolt ampere. The third one here that we have a huge transformer, 15 megavolt ampere or 20 megavolt ampere. It depends on the cooling system. So ONAN, oil natural air natural, 15 megavolt ampere, or oil natural air forced 20 megavolt ampere. So you'll notice in transformer nameplates that manufacturers typically specify ratings in volt ampere, kilovolt ampere, or megavolt ampere rather than power in watts. But why? A transformer is fundamentally limited by two quantities: the voltage it can safely handle and the current it can carry without overheating. So this is why you are going to say volt ampere rating equals rated voltage multiplied by rated full load current. This rating represents the transformer's maximum operating capability. The current flowing through the transformer windings produces copper losses, which cause heating. At the same time, the applied voltage determines the magnetic flux inside the core and influences core losses. So from the transformer's perspective, heating and insulation limits depend mainly on voltage and current and not directly on the actual real power consumed by the load. Hence, S, the apparent power or the rated volt ampere of the transformer equals V primary RMS value multiplied by I primary RMS value, which equals at the same time V secondary RMS value by I secondary RMS value. So if you like to calculate the primary current at full load equals S, which is the rated power, over V primary. If you like to calculate the secondary current at full load equals S, which is the rated power, over V secondary. Let us take an example. Consider a 50 kilovolt ampere transformer. If the load power factor is unity, meaning the load is purely resistive, then the transformer delivers 50 kilovolt ampere, which equals 50 kilowatt. So in this case, the apparent power and real power are equal. But now suppose the power factor drops to 0.5. The transformer is still operating at its full load rating of 50 kilovolt ampere, meaning the voltage and current are still in their maximum values, safe values. However, the real power delivered becomes 50 multiplied by 0.5. That one equals 25 kilowatt. So now the transformer delivers only 25 kilowatts even though it's fully loaded. This is exactly why manufacturers cannot rate transformers in watts. The watt output depends on the load power factor and the transformer has no control over that. Different loads can draw the same voltage and current but consume different real power. So voltage ampere rating gives a universal measure of the transformer's capability, independent of the type of load connected to it. Example: A 20 kilovolt ampere step down transformer, 500 volts in the primary side, 100 volt in the secondary side, is used to feed different loads. We need to calculate the primary rating current, the secondary rating current, and if the transformer is operating at full load and feeding an inductive load with a power factor of 0.8 lagging, what is the load impedance in the primary side and load active power? We're going to assume that our transformer is ideal. Given the rated power is 20 kilovolt ampere and the turns ratio is a primary voltage to the secondary voltage, 500 over 100 gives you 5 to 1. And that one is ideal transform. So the primary rating current is calculated using the equation I1 at full load equals S over V1. 20,000 over 500 gives us 40 ampere. Regarding the secondary current will be the same equation. So I2 equals S over V2. 20,000 over 100 gives us 200 ampere. Regarding the load impedance and the load power, we are going to have the voltage and current applied to the secondary side. Please note here that's operating at full load. So the current in the secondary side is 200 ampere, but 0.8 lagging power factor. So the current is 200 and angle minus cosine inverse 0.8. What is the voltage applied to the load? That one is ideal transformer. So the voltage applied to the load is 100 volt. So the 100 volts we are going to assume it with angle 0. So the power factor angle is the angle between voltage and current. So that one will be minus cosine inverse 0.8. Why minus? Lagging power factor. So the load impedance in the secondary side can be calculated as Z load equals V2 over I2. So that one is 100 angle 0 over 200 angle minus 36.8 gives us 0.5 angle 36.8 degrees ohm. The load impedance in the primary side we can use referring, so Z load dash equals A square Z load, so that one equals 5 square multiplied by 0.5 gives us the magnitude 12.5 ohm. What about the power? So the power equals voltage multiplied by the current cosine theta V minus theta I. So we are in the secondary side, V2 I2 cosine. Theta V is 0, theta I is 36.8 degrees. So the power equals 16 kilowatt. Let's check our answers. So Z load dash equals 12.5 ohm. So if we multiply that one by the current in the primary side, 40 ampere, that one is going to give us 500 volt, which is correct. And also the power, if we calculate the power from the primary side, 500 multiplied by 40 multiplied by cosine 36.8 will give us 16 kilowatt as well, like what we calculated in the secondary side. So our answers are correct. What will I watch in video number 4? In video number 4, we are going to cover the practical transformer. See you in the next video.